This time on Impossible Engineering, Extreme Railroads. Penetrating the great wilderness. Facing nature head-on.
This is really wild terrain. There's a more than 400-foot drop, and there's no escaping it.
With the solutions.
Like generations of Moormen before him, he looked to the ground beneath his feet.
That make the impossible possible.
This has got to be one of the most hard-fought pieces of railway engineering on the planet. This is magnificent. I love it.
Across the world, towns and cities are often separated by vast wilderness. Inhospitable landscapes, punishing terrain, and extreme weather can make crossing these divides seem impossible. But trains stop at nothing. Tackling previously uncharted territory with some of the most adventurous railroads on the planet. Overcoming the world's wilderness poses uniquely difficult challenges for even the most pioneering of railroad engineers.
Wilderness like this would stop any train in its tracks. This is an incredible feat of engineering.
So this is the start of the real climb. We're onto one of those tight curves. This is real mountain railroading.
It's bleak, it's isolated, it is utterly treeless. How can you build a railway here? What would you build it out of?
And it's one such seemingly impossible challenge that faced engineers in North America in the late 1800s. Promontory Summit, Utah is in the heart of the West. It's an empty desert landscape with few signs of civilization, as engineer Dan Dickrell is finding out.
Gosh, you know, there's really nothing out here. If you've ever driven across the western United States, there's these vast tracts of nothingness.
This particular barren stretch hosted perhaps the most significant moment in the history of the North American Railroad. Since the inception of railroads, engineers had dreamed of building a line that would connect America's East and West, and in 1869, that was about to become a reality.
Oh, this is a really cool moment. So I'm riding on the Jupiter, which is an exact replica of the steam locomotive that would have been here when the two railroads met from east to west. For the first time, you could ride from one end of the continent to the other. I can't describe to you how cool this is because this is a beautiful reproduction. It's in pristine condition. It weighs 60 tons, about 10 African elephants. It burns all of its fuel in about 30 miles, which is not a lot. It goes about 25 miles an hour. It's 2,000 gallons of water to make the steam. It's a huge but beautiful machine. Well, here it is. This is the Golden Spike. This is the location where the two lines met and were united.
But the circuitous mountain route added 42 miles to the trip. The more direct alternative route, however, presented some seemingly insurmountable challenges.
This is the Great Salt Lake. It is a mind-blowing sight when you're here. It's so massive, it's so vast. You can't see the other side. The sky and the water blends together. It's incredibly bright out here.
This phenomenal watery wilderness would present the railroad's engineers with an enormous task.
Standing in this spot, it's easy to imagine what those engineers felt so long ago trying to figure out how they're going to cross this vast body of water. It seems almost impossible.
But in 1902, engineers defied the odds and made a plan to build across the 1,700 square miles of exceptionally hostile landscape.
It's not even a bad day, and it's really choppy out here. The water is 6 times saltier than ocean water. Makes for a really dense and powerful wave. As an engineer, when you want to build something, you have to take into consideration the environment. And this is probably one of the most aggressive environments that you could build anything, right? Extremely salty water, high humidity, high heat in the desert. It's not a very hospitable place for something that's supposed to last for a long time. So I wouldn't want to build anything out here at all.
The monumental solution engineers came up with was the Lucen Cutoff. For a year and a half, 3,000 men grafted 2 earth and rock-filled embankments together, bridged in the middle by an immense wooden trestle.
This is the point where the old original trestle would have started extending out into the lake. It was 12 miles of timber. 2 square miles of forest were used to make this immense wooden structure.
In 1904, a train passed over the lake for the first time, cutting the journey through Utah from 10 hours to a mere 2 hours. But by the 1950s, conditions had taken their toll on the trestle bridge.
The pilings themselves weren't driven that far into the lake bed, and the lake bed in this particular lake is very soft. So the weight of the trestle itself, as well as trains, would cause subsidence. The trestle would sink. The aggressive nature of salt infiltrating the wood would cause it to split and deteriorate. Ultimately, it was decided that the trestle was to be torn down and replaced with something stronger.
Faced with such extreme conditions, engineers had to find a more robust solution. In 1956, work began to create an epic causeway that would carry the railroad across a raised stone embankment across the entire span of the lake.
This is the causeway. It stretches almost as far as the eye can see. Tons and tons of fill rock are dumped into the lake, something to build a track upon.
75,000 tons of rock were transported daily on 6 of the largest bottom dump barges ever constructed.
Seeing workers on top of the causeway gives a sense of the epic scale of this work, the size of the boulders, the elevation above the lake. It's massive. It's a massive structure.
But once again, Mother Nature showed her hand.
Now, these rocks and boulders that fill the causeway look large, but the forces that this lake can bring to bear are even larger. But it's a testament to how heavy this causeway is and how soft and squishy the lake bed is. It's always sinking, always subsiding. And so it's a continual battle to replenish this structure and a constant fight against the environment. That engineers, the rail line are continuing to fight, but it's tough. It's a tough fight.
And crucially, culverts that had been built to allow water to flow through the causeway had cracked to the point they could collapse and take the track out of service.
Due to the nature of this extreme environment, those culverts were folded upon each other. They were consuming it. Didn't work.
To keep trains running, the cracked culverts were filled in. But what happened next was unprecedented. Blocking the flow of water created a startling difference in salinity, water level, and even color.
So the engineers had to come up with a different plan, a different solution that ultimately would enable the lake to breathe its water and allow railways to move.
In 2016, this clash with nature inspired another incredible feat of engineering.
So this is the brand new bridge that engineers hope will solve the causeway's problems once and for all. The new pillars are driven 200 feet down, even though the lake's only 35 feet deep. The pilings themselves are a steel core covered in a special material to prevent effectively environmental damage, eroding and destroying the columns. See, as we pass underneath the berm here, this allows the railway to add and remove material to help flow control in between the northern and the southern parts of the lake. The northern part's much saltier, so the water exchanges through. Wood couldn't make it, concrete couldn't make it, so hopefully this is the solution that will solve these problems from a material science perspective for the railway.
This watery wilderness baffled engineers for decades. But despite the struggle, the railroad ultimately won.
This has got to be one of the most hard-fought pieces of railway engineering on the planet. Nothing but respect for the people that keep this line in service in such a tough place. Oh, what a cool sight to watch this actually happening on the Great Salt Lake. Oh, this is awesome.
But harsh environments come in many forms. In New Zealand's North Island, for example, is an epic wilderness of impenetrable rainforests and soaring volcanoes. A terrain completely inhospitable for a new railroad. But the innovative minds behind the main trunk line weren't about to take impossible for an answer. In the late 1800s, engineers were trying to connect New Zealand's two major cities, Auckland and Wellington, by train. But there was one spot on the route where progress reached an impossible impasse. Amongst the rugged, overgrown wilderness was the Central Plateau. Local railway expert Paul Mahoney is taking the railroad to this challenging location.
I'm at Otorohanga Railway Station, about to get the train down to Raurimu. This railway was surveyed from the north and the south, but for 14 years, Raurimu was a sticking point for engineers.
But in 1898, it fell to engineer Robert West Holmes to conceive a plan to surmount the wild landscape. However, it wouldn't be as simple as carving a path through the untamed bush of Raurimu, as heritage advisor Karen Astwood is discovering for herself.
When engineers were trying to make a railway through this area, they had such a lot of trouble. It was a real nightmare. Coming down from the Central Plateau, there's a more than 400-foot drop, and there's no escaping it.
Faced with a distance of just 1.2 miles in which to negotiate the steep rise between the valley and the plateau, the gradient of 1 in 15 would be too extreme for standard locomotives.
The only way to make it up that gradient in a train would be to use specialist trains, but the cost of maintaining those was simply too prohibitive. There was talk that the line might have to be rerouted. The government didn't want that. They'd already spent enough money on the project. Overcoming the wilderness here was seen as the lesser of several evils.
Even riding the rail link today, the journey is a reminder of what Holmes was faced with.
This was covered in a thick native forest. It's very rugged country. Here's the sort of forest they were working in.
With help from technology that Holmes could only have dreamed of, Karen is getting a bird's eye view of this uncultivated landscape.
This is really exciting.
And from the sky, the extraordinary solution that Holmes came up with can be viewed in all its glory. The Raurimu Spiral.
What we can see below is one of the most ambitious and brilliant pieces of wilderness engineering in the world. Here comes a train So we're going to be able to see Holmes's masterpiece in its full glory.
Following an intricate route, the single track snakes its way around to lengthen the line at a shallow gradient.
The Raurimu spiral is really impressive and complex set of elements, which is really compactly put together.
But Holmes's masterpiece was anything but straightforward. The spiral twists and tunnels under itself, up first through a giant horseshoe curve and then a pair of tight quarter turns, before winding around on itself in a complete circle to reach the plateau. It extends a distance of just 1.2 miles as the crow flies to create a track over 4 miles long. Seeing the spiral from Holmes's perspective reveals the curves close up.
So this is the start of the real climb. We're onto one of those tight curves. They're 150 metres radius, and we're on a 1 in 50 grade. This is real mountain railroading. They had to put this railway to the landscape, and it was very dense forest here, so they couldn't actually see very far to do the surveying.
A problem made worse by the treacherous terrain, which gave Holmes no natural vantage points to plot a route from above.
There was no way he could get to a high point to see how the land was set out. He had to do a lot of exploring to create a picture in his mind of what the terrain was like. So this is an amazing railway location achievement.
These days, engineers would carry out an aerial survey and simply take to the skies.
All the loops and curves, even the small ones, were really critical because they lessened the wear and tear on the trains and on the track as well.
But mapping a route wasn't the only challenge that had to be overcome to pull off this audacious build.
So coming out of tunnel number 2, we're more or less halfway round the spiral now. Looking back, you can see just what rugged country this is.
Carving a path through the impenetrable forest, steep ravines, and sheer cliffs had to be done by hand.
So the spiral was entirely constructed by pick and shovel and some dynamite blasting. And this is a high rainfall area. The workers lived in tent camps, and it was pretty tough going. What an achievement.
In 1908, the first train traveled down the Raurimu spiral. Almost 4 decades after the North Island main trunk line was first conceived. Finally taming what had seemed like an insurmountable wilderness. Over a century later, it's still considered one of New Zealand's greatest feats of engineering.
This must have been so complex to try and lay out, and it really is just a tribute to Holmes's genius and also the engineers that he worked with. It's spectacular.
80 years after Holmes laid out the spiral, Horace Riding was the chief civil engineer of the railways, and he'd been involved with trying to improve the route of the railway ready for electrification. And the modern engineers were still not able to improve on George Holmes' spiral location. It's a masterly piece of engineering that survives to this day.
But imagine the challenge of building one of the earliest railroads in Britain. In Devon, in the southwest of Britain, sits a huge expanse of harsh, magical, and ancient landscape.
This is Dartmoor National Park, which is just shy of 1,000 square kilometres of amazing wilderness. It's full of ponies, rolling heathlands full of gorse, and its most famous export, granite.
And in the 1800s, that granite was in demand. With the British Industrial Revolution at full steam, buildings were getting taller, Bridges were getting larger, and engineers were looking close to home for supply to meet the ever-increasing demand, as historical archaeologist Cassie Newland is finding out.
You can really see around here that the granite just sort of comes out of the ground. It's everywhere you step, everywhere you look, which is why people have used this resource in this place for thousands of years.
Dartmoor might have been full of granite for almost 300 million years. But in 1820, the enormous challenge would have been building a transport system to get the rock to civilization.
It's bleak, it's isolated, it is utterly treeless. You can go from frostbite to heat stroke in a blink. How can you build a railway here? What would you build it out of?
Entrepreneur George Templer decided he could defy the odds and build a railroad to transport goods from his quarry at Haytor. But it was the intrepid railroad engineers he called on who would have to make his plan possible. Nineteenth-century entrepreneur George Templer needed a way to transport vast quantities of granite from his isolated quarry to the building projects that needed it.
This idyllic little oasis is actually Haytor Quarry, and it would have felt incredibly different 150 years ago. We'd be surrounded by bustling men hard at work, drilling holes and blasting with dynamite to take vast chunks of granite out from the cliff walls. The air would be thick with dust. It would be completely unpleasant. Just behind me, if you can see the log in the pond, that log is actually the base of a derrick, a kind of crane that would have been used with the winch that you can see in the background to lift these huge blocks of granite. So you would turn this handle, and it would crank a cable which would lift up the arm, your jib arm of your crane, which is just over here. And if you're very careful and don't fall in, it's this huge, huge length of wood with a socket at one end through which all your winching gear would pass, right the way down to the base over here, which would fit into a metal socket in the ground and allow you to pivot around to lots of different points in the quarry, lifting the stone that's blasted off from the side to places that can be worked, and also lifting it onto the wagons to take it away. So the challenge of Haytor is getting the granite out. But at 1,300 feet above sea level, with no other natural resources, it is an impossible challenge.
Templer had realized that building a track out of the quarry was the only option.
Like generations of moormen before him, he looked to the ground beneath his feet and he built the railway from granite.
This engineering marvel born out of the ground is the Haytor Granite Tramway. Amazingly developed to transport the very granite that it was made of from the quarry to a canal for distribution.
Now this rail here is the perfect place to see how skilled and arduous a job it is to produce a granite railway, because using a chisel and a hammer, you've got to cut this lovely precise line right the way along your rail for the wagon wheels to run in. The one good thing about having invested all that time in creating a granite rail is you don't then need sleepers. The stone itself is so heavy it holds it in place. Now, granite is incredibly hard. The man-hours that go into taking out a slice of granite like this are incredible. And if you think you do that over 10 miles worth of railway, the labour is extraordinary. The first thing you've got to do is split your rock into manageable chunks. And you do that using a feather and tear method. And these slots here are remnants of that process.
The ingenious feather and tear method is still used today, though made much easier with the help of modern tools, as demonstrated by Dartmoor National Park employees Lee and Andy.
Well, what we're doing here, we're drilling a line of holes down the length of the granite where we want the split to be. Now, the next stage of the process here is to use the feather and tear tools. Two types of tool here. We have this metal iron chisel, which is the tear in the process, and these two thinner strips of iron, which fit down the side of it in the hole. Once you've got this arrangement in the hole, if you hit this on the top with a hammer, it will force it down and force the granite sideways. If you do that in each of the holes along the length, eventually the stress will cause the granite to split along the line we want it to. That's not going anywhere, so that's ready for the next stage. That's it. We have now successfully split the slab exactly where we wanted it to. Shows it's a very effective and quick technique, really.
This astounding feat of engineering is made more impressive by the speed of its construction, precipitated by an important commission.
So as soon as George Templer had won the contract to build London Bridge, he had to get this railway in as quickly as possible. The quarry opened in 1819, and this railway was opened by 1820. That is an astounding feat of will.
But solving the challenge of building this railroad is only half of this incredible achievement. As steam locomotives had only just been invented, Templer used the more common engine of the day, good old horsepower. The problem was how to avoid your prized equine engine getting crushed by a load of granite.
So gradient is always an issue for every railway. But here, where you've got just regular wagon wheels, running on grooves, cut in stone, it's a particular problem. Instead of the horses pulling the wagons, what they effectively have is the horses braking the wagons from behind, and up to 12 wagons, each of them carrying 3 tons of granite, being sort of slowly lowered down the hill on these rails.
And bringing 40 tons of granite to a stop on an incline is no small task. But the solution would help to build some of Britain's most iconic structures. The engineers responsible for laying a track that would transport granite from Templer's mountaintop quarry had a major problem to solve: how to slow the wagons when horsepower alone wasn't enough. With the dramatic inclines along the way and tons of granite on board, it was crucial to develop a dependable braking system.
So you've got the horses behind, but for tricky bits where there's an incline or points, you've got a man with a stick, a 12-foot pole that he jams against the wheels as an extra brake. The whole thing is at the absolute limit of human skill and ingenuity. And the reason the horses went down was not just to brake it, but to pull the wagons back up the hill from the other end. So it's all thanks to Templer's pragmatic solutions that the granite from the high tors can now be found in some of our most iconic buildings. Nelson's Column, the British Museum, London Bridge, and it's all down to this perfect yet simple railway.
It's another tenacious solution to reach into the wilderness. But for some remote railroads, it's about connecting civilizations. Covering an area greater than Western Europe, the Tibetan Plateau in Asia is the largest and highest plateau on Earth. With drifting sand dunes and alpine wetlands, temperatures swing from a bone-chilling minus 40 degrees in the winter to a sweltering 86 degrees in the summer. It's a treeless and windy wilderness. At first, this seems like the last place on Earth for a railroad. But the Qinghai-Tibet Railway has taken on this challenge. For a century, China had dreamed of connecting with the inaccessible region of Tibet. In 1974, work on a railroad began at Xining. Cutting across the rugged northern edge of the plateau east to Golmud. When engineers tried to head south to Lhasa, they encountered a seemingly impossible obstacle. Nearly 350 miles of unstable terrain, with a permanently frozen layer below the surface, known as permafrost. Senior engineer Mr. Jinsheng Wang was part of the team in charge of finding the solution.
Permafrost is a mix of soil and sand bound by ice with a temperature that remains below zero for at least 2 years. If the frozen soil is always below zero, it will provide a solid and stable foundation for buildings above it. However, the surface layer can melt and its load-bearing capacity can decrease, damaging all the architecture above.
Without solid land to lay a track on, engineers had to find an innovative solution.
So we built a bridge instead of laying tracks.
This is the Qingshuihua Bridge. At over 7 miles long, it is the longest bridge over permafrost in the world. To make it a reality, engineers had to dig deep enough to reach the solid base below.
So there must be 4 piles beneath every pillar. The pile foundations are 20 to 30 meters deep.
To reach those depths, a rotary digging machine is used. The holes are then filled with concrete, but as heat is released by a chemical reaction during the concrete mixing process, the danger is damaging the permafrost. So the work needed to be completed during the harsh winter months. But to set and strengthen, concrete must be kept above 50 degrees, which means it has to be heated before it's poured. So chemicals are added to the mixture to help speed up the setting process and safeguard the permafrost. This phenomenal bridge spanned the most difficult section of the Qinghai-Tibet Railway and enabled engineers to finally complete their journey across the plateau.
Building a railway under extreme weather conditions on the Qinghai-Tibet Plateau is 10 times more difficult than building a railway on normal solid ground.
It took an army of more than 600 medics and 17 oxygen stations to support the construction team. Reaching altitudes of over 16,400 feet means that oxygen is 45% lower. Today, just traveling the route gives a real sense of the conditions that the workers faced. Even passengers on this highest stretch of rail need to have access to oxygen. Completed in 2006, the railroad was mainly used by tourists visiting the once isolated region of Tibet. Today, it's a vital part of everyday life for the locals, with the number of trains almost doubling in just over a decade. But none of it would have been possible without the Qingshuihua Bridge.
Being part of the operation and management of this worldwide engineering project is my glory and my duty.
Permafrost might be a formidable opponent. But around the world, railroads must cross many different landscapes. And one that presents an altogether different challenge is a forested wilderness. Steep inclines and dense foliage once stood between the California lumber industry and its ability to meet skyrocketing demand for building materials in the 19th century. But the engineers behind the Sugar Pine Railroad at the base of the Sierra Nevada mountain range were prepared to make the impossible possible. In the late 1800s, fueled by the gold rush, the demand for timber across North America was sky high. Thick pine forests on the western slope of the central Sierra Nevada wilderness offered an abundant supply. Horses and oxen were the usual method of transport, but to meet demand, locomotives with their superior power began to appear. But getting them through thick forests was far from easy. Engineer Chris Potts is at the site of a once prolific logging operation.
This is the Sugar Pine Railroad, located in California's Sierra Nevada forest. And these surroundings are what would be typically seen in the early logging camps. These tracks here are actually quite modern, made of steel, sturdily fixed into place, and well maintained. The difference is that the early railroads would have had no such luxury. Earlier railroads were made of the logs they milled. The tracks would have only ever been temporary.
Quickly laid temporary tracks would weave their way through the trees. The track's tight curves and makeshift nature were a recipe for disaster for the recently introduced rod locomotives. These huge trains were powered by pressurized steam, with their horizontally mounted pistons driving only a single set of wheels. With all the power from the engine concentrated in a small area, it meant poor traction and a limited ability to climb gradients.
This is a rod locomotive's worst nightmare. They could only travel about 4% grades at their max, and this right here is about 12%, almost 3 times as much as a rod locomotive could usually go on. With the rough terrain, the tight curves, and the steep grades, rod locomotives would have a hard time making it here.
But it's not just the terrain that the engineers were battling.
When the rod locomotives went down the track, the action of the piston moving back and forth would have easily tore the tracks right out of the ground. If locomotives were going to make a positive impact on the logging industry, the rod engine would have to be completely rethought.
And in 1877, entrepreneurial logger-turned-inventor Ephraim Shea proposed a solution with the introduction of his radically redesigned locomotive.
This is incredible! I'm riding the number 10 Shea, the largest narrow gauge Shea ever built. Standing up here, you can truly appreciate the power, the steam, the heat of the fire, and the pistons moving up and down. What a feat of engineering. Absolutely incredible.
This is a Shea Lima locomotive, and it's impressive beyond its mighty power.
At first glance, you'd be forgiven for confusing the Shea with a rod locomotive, but actually it was a revolution in design. It completely transformed the locomotives for the logging industry. Wilderness like this would stop any rod train in its tracks, but not the Shea.
In fact, the innovative design making this locomotive move changed the lumber industry. So just how did the Shea help make the Sugar Pine Railroad a reality? Engineer Chris Potts is discovering how Ephraim Shea's revolutionary locomotive design enabled the Sugar Pine Railroad to take on the dense woods at the base of the Sierra Nevada mountain range. The key to Shea's design is that instead of using rods to power just one set of wheels, it uses gears to share the power between 6 sets of wheels. It's a fundamental change that transforms how a locomotive uses its power and gives the Shea its unique appearance.
This is how it works. There are 3 giant pistons, and these massive pistons work in a vertical direction. As the power generated by the steam from that boiler is transferred into this gear train, it is sent down to the bevel gears, and these gears work with a 2-to-1 ratio, where the smaller gear spins twice as fast as the larger gear. And the way it works is it takes that speed from the smaller gear and transforms it into torque, meaning that this train can go up 14% grades unheard of for trains of its age and can take huge loads across huge distances. There's a bevel gear on each one of these wheels, essentially making it a 12-wheel drive. Pretty cool.
By realigning the cylinders and gearing the power to each set of wheels, Shay also had increased traction and would be far better suited to the demands of the challenging logging landscape.
So one of the key differences here is that this train operates with 3 vertical pistons, meaning that it was a lot less destructive than the rod locomotives of its time, where they operated with a horizontal piston, meaning that it was less destructive to the tracks.
After its introduction in 1878, the Shay locomotive was an instant success story, enabling these relatively small engines to move heavy goods at low speeds through rough terrain. Over the next 10 years, more than 300 Shays were produced, totally transforming the logging industry.
The Shay train was perfectly equipped to brave even the most challenging of wilderness. This is an incredible feat of engineering. Just the sheer power. I love it.
For centuries, railroads have carved paths through the world's most unforgiving wilderness. Through exceptional creations.
It's spectacular, and you don't find this type of thing in many places in the world.
It's rainforest railway engineering at its world's best.
And cutting-edge solutions.
Someday they'll have to build a train on Mars or the moon or whatever, but this is about as close as that gets on Earth.
Engineers continue to succeed, creating impossible railroads.
Engineering versus the wilderness, I think engineering won.